So we'll just kind of keep building on what we've been talking about. We're going to focus on, I call it sludge. We're going to focus on basically some things that aren't insoluble. Now, among different chemical reactions, there's this one chemical reaction called an exchange reaction, and this is where the cations switch partners with the anions. So you're going to see what I mean here in a minute. So, for instance, we have two reactants, and the blue here, that fancy font means it's a cation. The red means it's an anion. So we have two salts. We call it a salt if it's an ionic compound. And then can you see the difference on the product side? So the cation that used to be with B is now with D, and the cation that used to be with D is now with B. So they just switched. Now, the way this intersects with what we've been talking about is that over here on the product side, if I could put an S next to either one of these, that means S means it's going to precipitate. It means it's a solid. It means it's insoluble. Okay? And so that's the sort of thing we're going to be kind of talking about. Okay? So if you see a sludge formed when you mix two things, right? So I've got some examples to show you. Videos! For the exchanges, and I know Lindsay was just saying before class, it's like, it's good to remember. So for instance, in Chem 1 we talked about that's hydroxide, OH minus. Okay, so that's actually, that anion, polyatomic anion is going to go with the cation. So you'll have your iron 3 hydroxide. And here's where actually, if you look at iron 3 hydroxide, the S means that that was the yellow precipitate. The other thing is, remember, you have to write a neutral formula unit. Hi, Rhonda, welcome. So neutral formula unit, we know this is an iron plus 3 cation because over here, these chlorines were -1 and there were 3 of them. So that's a +3. These are each -1s, collectively -3. So over here, if it's a +3, when we're combining with our hydroxide, which is each of -1, we need 3 of those to make a neutral formula unit. So that's the Chem 1 stuff that we talked about, and that's still fair game. This is a balanced exchange reaction. Now, I'm going to go ahead and give you a heads up too. Working this sort of problem, what we're going to do is, this is our chemical reaction, this is our exchange reaction. Here in a minute, we're going to isolate this special guy, the product guy with an S, the precipitate guy, and we're going to actually write the chemical equilibrium of that. So it falls into a pattern. And write the balanced exchange reaction, take the guy that's insoluble, and write the chemical equilibrium for him, or her, whatever. Okay? So let's look at another one. This one's going to be silver nitrate, 2 clear solutions, silver nitrate, sodium chloride, mind your own business. And actually, I think this is what you guys did in lab, maybe, that the thing that's going to precipitate is the silver chloride. And then sodium nitrate is still going to be soluble in there. Okay. All right. Let's see what this looks like. As I was getting ready for today's lecture, I'm like, oh man, it's those darn solubility rules. So again, before you come to your test on Thursday, I would take a look at the solubility rules, whichever we want to look at. Remember, OpenStax has their nice little table. But if you look at the solubility rules, you're going to see that lead 2 chromate is insoluble. That's the yellow. So actually, in this exchange reaction between lead 2 nitrate and potassium chromate, they switch partners and look for the S. Okay, lead 2 chromate. Another one. This is a kind of a cool looking precipitate. Okay, lead 2 nitrate, ammonium sulfide. Let's see, it looks like the lead 2 sulfide is the thing that's going to be precipitating right here. So again, you want to be able to, kind of like we did in Chem 1, take these 2 salts and be able to switch cation and anion, put them on the product side, but go ahead and balance it. Okay, notice it's balanced for the same number of atoms of each type of element on either side of the reaction arrow. Okay, one more. So what's the precipitate? FeOH3. Yep, iron 3 hydroxide. Exactly. This one doesn't even really look like a precipitate. It looks pretty clear, but it is. Another one. What's the precipitate here? Silver. Yep, silver chromate. Yep. So already in the back of your mind, start thinking, and you can't put too much information if you're working a problem. You know, I call it doodling. Just put down information and see, do I need that? But working on an exchange reaction like this, write down the first exchange reaction, and then you're going to write down the equilibrium of the thing that has an S next to it, the insoluble salt. Okay. Now, as we kind of talk about these precipitates forming, in general, we say a solution is saturated if it's saturated if it's right at saturation if no more can dissolve into it. And by golly, if you see a precipitate, then you see the sludge down here, the solution above it is saturated. Okay. And the word dynamic means that you still have solid sludge pieces dissolving and you have dissolved pieces precipitating. It's dynamic. They take turns dissolving and precipitating. All right, so I got a couple examples to work then. Let's go ahead, we got time. I'm gonna draw a picture, see if we like do it that way. Because I just think I would always draw a picture of this. Okay, so 1.20 grams of NaCl is going into 100 milliliters of, oh, it's not water, is it? 0.012 molar lead 2 PbNO3 2. Now, I know it seems like a busy sort of thing, but even before I go to work the problem, what I'm hoping is that you guys can take this guy right here and recognize that this is how I think of it. Pb quantity NO3 2. Oops. It's going to separate, and it's going to give Pb plus 2 and NO3 2 minus. I'll go ahead and put a 1 here, a 1 here, and a 2 here. Help me out. If this is 0.012 molar, what's the molarity of the lead 2? 0.012 molar. What's the molarity of the nitrate? 2 times it, yep. 0.024 molar. You know, it's a real common mistake, but that's kind of what we have going on here. So the question is, and actually for some of your problems, you won't have to know solubility rules. But the solubility rule is that if anything is going to precipitate, it's going to be your lead 2 chloride. So bottom line is we already have lead here. We're adding chloride in the form of sodium chloride. Sodium's a spectator ion, and it looks like nitrate would be a spectator ion. Okay. So will a precipitate form? And we have the solubility product constant, the KSP, for lead 2 chloride. So this is what I was saying. I really think, and sometimes on my test, I draw and make you do this. You need to write the balanced chemical equation for the exchange reaction. So we have 2 NaCl plus PbNO3 2 goes to form, and to balance it, it will form 2 NaNO3 and PbCl2. And for sure, I would put an S next to the PbCl2. I might, be sloppy. I might not put my AQs, but I'm definitely going to put an S next to the PbCl2. So be able to write that balanced equation. All right. So I said this was coming, so we're going to take the PbCl2. We've been talking about how you can write its dissolving process, basically, is what it is. So PbCl2 solid will dissolve sparingly, be in equilibrium, and make sure we write it balanced. It'll break apart and give you 1 Pb plus 2, and it will give you 2 Cl minuses from the formula. One of the things about chemical equilibria is we can write an equilibrium constant expression. This happens to be a special one, it's KSP. It's always products over reactants, but anything in solid state does not appear. So your KSP expression looks like this. KSP then, which we were given the value of, is the molar concentration of the Pb plus 2 raised to the first power times the molar concentration of the Cl minus, the chloride, raised to the second power. And again, we were given a value for KSP in the problem. So I bet you're kind of, because you guys have been working these problems, you probably have a sense for it now. Because we know your lead 2 molar concentration, you guys told me that was 0.012 molar. We can get your chloride ion concentration. We'll have to do some Chem 1 techniques, but we can use this, the salt that we're dissolving, in the volume we're dissolving it, to get the molar concentration of chloride ion. We plug it in there, and remember the good old, the snapshot? We're going to do a QSP compared to KSP and see what we got. All right. So yeah, and I wish I'll grab the pen. The difference between KSP expression and QSP is what I've been saying is a snapshot. It may, that's an SP, it may or may not be at equilibrium. Okay, so that's kind of our overall thing. Got a few steps to get to this point. So if they happen to be equal, you're right at the kind of the tilting point. If our QSP is equal to our KSP, which we were given, then we're right at equilibrium. Now we said if it's too small, what will happen? If your QSP is too small? Yes, it'll go to products. And then I always have to think, now what are products? Well, products were my dissolving stuff. So if it's too small, it's going to keep dissolving more. It's undersaturated. Very good. And if it's too large, what will you visually see? Go back to reactants, and so what will you see? The reactants are the solids, so what will it look like? It'll be beyond saturation. What are the videos we just saw? They'll turn cloudy. Yep, they'll turn cloudy, exactly.
So more reactants, so more products. Oh, more solid, so it sinks down to the bottom.
Yes, okay. Yep. Because the reactant was the solid, and the product was the dissolved part. Yep. So this is one of those things that I think I don't memorize. Good, bad, or otherwise, kind of think through it again. All right, so here we go. There's our equilibrium of interest. So, yep, a precipitate will form if our QSP is greater than our KSP. So, however you want to remember that, that's the deal. And again, I'm not good at memorizing, because about the time I memorize, I get it wrong. Like, oh, okay. All right. So, now when we work a problem like this, we're going to assume that we're just going to add all the NaCl, we're going to do it stepwise, and then we're going to evaluate to see if precipitate forms. So when this says, what's the chloride ion present, it's assuming before any precipitate. The other thing we're going to assume here is that that 1.20 grams is not going to include or increase the volume of that water. Because remember, molarity is moles per volume of solution. So, all right. So yeah, we got our lead 2 is 0.012 molar. And our initial chloride ion concentration isn't anything before we add our sodium chloride. We're not going to make an ice table for this though. Sometimes students, when they take this unit exam, they're like, now, do I use an ice table? No, no ice table for this one. Okay, so what would that chloride ion concentration be? So this is kind of where I'm going to knock this out. Again, I'm not going to show you how the molar mass of sodium chloride, my bad, but we're going to have to use it. So we put 1.20 grams of NaCl over our 100 milliliters of solution, 3 sig figs. The molar mass of sodium chloride using the periodic table is 58.44 grams per mole. So if I put 1 mole of NaCl in the top and the 58.44 grams of NaCl on the bottom, the grams of NaCl cancel and I have moles of NaCl per milliliter of solution. I need a few more terms there. And then after the molarity of the Cl minus. So then if I introduce another term, it doesn't have to be in this order, that for every 1 mole of NaCl, I'll put that in the bottom, I get 1 mole of the Cl minus. What else do we need to fix? Yep, to liters, you got it. So one last term, because molarity needs to be in liters. So if I introduce 1,000 milliliters over 1 liter, now things have canceled, and I have, grams of NaCl cancel, moles of NaCl cancel. We're left with moles of chloride ion, and milliliters of solution cancel per liter of solution. Perfect. So 3 sig figs looks like 0.205 molar or moles per liter of Cl minus. So now I've got that ready to plug into my KSP expression along with my lead 2 ion to see if my QSP is larger than my KSP. So it looks like this. So you have 0.012 raised to the first power, that's your lead 2, times 0.205 raised to the second power, that's your Cl minus. And we get 5.1 times 10 to the negative 4th. Is that larger or smaller? Larger, yep. Sometimes it makes my eyes go buggy a little bit, but it is larger, yep. So I have to kind of concentrate on this power of 10, I'll get you. Yep, so since it's larger, how many people think a precipitate will form? How many people think a precipitate won't form? How many people think a precipitate will form? There you go. Yep, precipitate will form. Exactly. That's it. It's like, this is a weird sort of problem because it's like you have a 50-50 chance of getting it right. So sometimes when I'm grading people's test questions, I'm like, you had a 50-50 chance of getting it right, but don't just guess. And some of you guys have very good intuitions. So.
It's probably the 1/2 hour. Hey, it kind of plugged in. It kind of works. I'll go with it.
Yeah, he likes it. So that works. Okay, so let's do another problem. And like I said, we're not going to worry about tackling the third problem today. Oh, but I meant to, and I will push it out for I'm seeing tomorrow. I will push out the solutions for the third problem, just in case you. All right. So this one, let's draw a different picture. I just think some problems really help if you draw a picture, and they help sort things out. I'm not always stalling, but okay. So in a common beaker, I have a couple of solutions of salts. Okay, this side, I'm going to put 200 milliliters with 4 sig figs. 0.350 molar K2CrO4. No, is that right? Okay. And then we're going to mix it with 200 milliliters of 0.0100 molar AgNO3. You know, and you might even, you know, every time you work or I work problem, I do it differently. I might even kind of do like I did before. I'm going to go ahead and show that this is going to dissolve, and I'll go ahead and say, yeah, K2CrO4 is going to break apart and give me what, 2 K pluses and 1 CrO4 2 minus, and the molarity was 0.350. You got plenty of time on your test. So what would the molarity of the K plus be?
0.00.
Yep, 0.700. How would the molar concentration of the chromate? Yep. Doing it over here, my AgNO3 is going to break apart and give me Ag pluses and NO3 minuses. And I have 0.0100 molar. So what's the molarity of the silver? Yep. And what's the molarity of nitrate? Same. Yep. You know, and you're like, do I need to do that? I don't know. This is, you know. And then if we read it, it says, will it precipitate form? Now, just off the top of your head, actually, I don't know if it's probably on the next slide. So what we're doing is we are mixing these two guys, these two things, K2CrO4 plus AgNO3, they're switching partners. I'm not going to balance it yet, I'll get to that. So your potassiums are going to go with your nitrates. Now here's where you have to remember the charge of your potassium. Like that's the one you get out the periodic table. It's +1. Your nitrates -1. And you're also going to end up with what? Silver AgCrO4. But the thing here is I know my CrO4 is a -2. So I'm going to have to put a little 2 there with my silver, which is a +1. Is that balanced? No. How about if I put a 2 here, because everybody balances it differently, but if I put a 2 there and a 2 here, I'm kind of liking that. What do you guys think? Okay, so be able to kind of do that.
2 minus doesn't go up behind the CrO4. You just put it
Right
down there to the Ag.
Yep.
Because the
Yep.
crisscross thing.
Yep. Yep. I think I understood your question. You answered yours. Yeah. Yeah. So just off the top of your head, what do you think? Because I'm curious, because I've been doing this for a few more years. Which one of these two would be a solid, potentially? How many people think it's the first one? How many people think it's the second one? You're right. Why did you think the second one?
Chromate.
What's that? Because it's
Silver
chromate.
chromates.
Sounds like a solid.
It's probably on one of those rolls.
Probably in one of those rolls. Another one, this might have been subliminal, but the follow-up question says, what percentage of the silver would be left after precipitation began? And again, so that kind of shows you, you know, that this is the character. So very good. Got good instinct. I'm just saying. Right? Exactly. Okay, so let's work these problems. Will it precipitate form? Well, you know what, and I won't put it up here, but you know what we're going to have to do is we're going to have to take the Ag2CrO4 and write its own equilibrium. I'll put this all up there. This is the pattern you need to do with these. The top one is the balanced equation we did over here. That's from the exchange. Notice the one-way arrow. No chemical equilibrium. And then the second is to run with the insoluble salt. So the second down here is to take the Ag2CrO4 in equilibrium and from its solid state into its dissolved state. But you have to keep your wits about you and make it balanced. Yep. It's gotten a lot of us because once you balance in that changes everything because we're going to raise it to the power of its stoichiometric coefficient.
So you don't drop the pluses and the 2 minus until you're breaking down the salt.
Right. Yep. The plus, the 2 minus or in the plus, it does not appear when it's in its salt form. It appears in its broken apart form. Yep. Okay. So game plan is going to be to compare that, just like we did before. We're going to come up with a QSP and compare it to KSP. So not too bad here, right? There is one catch though, and it's going to be here. Let's see. So there's this guy, right? And this guy. The catch is this. We need the molar concentrations. We have to remember what this is talking about. This is 200 milliliters of this molarity doused in, what's the total volume? Yep. 400 milliliters. That's your total volume. So basically what you're going to see here on the slides is we're going to go back to Chem 1 toolbox and we're going to use the volume molarity to get to moles. And we're going to divide those moles by that volume. That's what we're going to have to do. That's it. All right, here we go. So as far as your chromate goes, over here, the moles added, we used the volume, which was 200.0 milliliters, and the molarity. Oops, sorry, it looks like my second term here is to get it into liters. So we can get into liters by taking 1 liter over 1,000 milliliters. And then we can introduce molarity, which was 0.350. So 0.350 moles of the whole salt. 0.350 moles K2CrO4 over 1 liter of solution. So that's the molarity. So how are we going to get to moles of CrO4 2 minus from this? So if we introduce just a 1 mole of CrO4 2 minus over 1 mole of K2CrO4. Giving ourselves 3 sig figs. It looks like the molarity, or this isn't the molarity yet, is it? Giving yourself 3 sig figs, the moles of chromate, CrO4 2 minus, is 0.0700 moles. Again, now to finish up, we have to take those moles and divide by 400 milliliters, basically. All right. So before we do that, let's go to the other side, so the silver ion. Do a similar pattern. So we had 200.0 milliliters of that solution. Go ahead and convert it to liters. 1 liter over 1,000 milliliters. If we introduce molarity as our next term, 0.0100 moles of the salt, so that would be moles of AgNO3 over 1 liter of solution. How do we get from moles of AgNO3 to moles of Ag+? Stoichiometry. 1 mole of Ag+ over 1 mole of AgNO3.
So you can't just start it out with the Ag+ instead of doing the stoichiometry and the table.
Yeah, you probably could. I would be fine with that on a test. She's saying, can I just go ahead and think this through. Just be careful. So, yep, you could. So 3 sig figs, you're looking at the moles in that 400 milliliters is of moles of silver is 0.00200 moles of Ag plus. So, yep, the total volume is 400 milliliters because we had 200 from each of our solutions. This is why I think if you draw a picture like, oh, okay. So to finish things up, then the molar concentration of the CrO42 minus would be the moles we found, 0.0700 moles, divided by 400 milliliters. But that will give us moles per milliliter. We need moles per liter. So then we have to introduce 1,000 milliliters over 1 liter. It's a lot of work. And this is all to get a value to plug into our QSP. So 3 sig figs, the molar concentration of your chromate ion is 0.175 molar. All right, we'll do a similar thing for the silver ion. So in that case, we came up with 0.00200 moles of Ag plus, again divided by that 400 milliliters of solution, 4 sig figs. Clean it up by introducing 1,000 milliliters over 1 liter. Round to 3 sig figs. And we get 0.00500 moles per liter of the silver ion. Very good. So you know the drill. We're going to plug these guys back into our QSP expression, see what we got. So QSP, now the whole square will get us. So QSP is the molar concentration of your silver squared times the molar concentration of your chromate ion. So I get this. QSP is 0.00500 squared times 0.175. And 3 sig figs, I get 4.38 times 10 to the minus 6th. So, is this larger or smaller than our KSP? Oh, yeah, we got them right there. That helps. It is larger. So, how many people think a precipitate will form? Me too. Yep. I guess it's not too bad to memorize. If it's big, it'll, I don't know, you can precipitate.
Could you go back one slide? There's something I didn't quite get.
Sure. Now, there is a follow-up question. And the follow-up question is, how much of the silver chromate will precipitate? We're assuming that it's beyond saturation. And we're also assuming that since the molar concentration of the chromate ion that we came up with is significantly larger, that's what the double greater than means, significantly larger than the silver ion, then basically all of the silver ion will be consumed. So that only the silver ion that remains, see, this seems like, when I get to this problem, like, really? The only amount that remains will be that's in equilibrium with the remaining chromate. So to work that follow-up problem, question that looks like this. Moles of the chromate ion that precipitated can be found this way. Assuming that the chromate that precipitates is going to be driven by the silver that's present, and all the silver is going to precipitate, then we know that the moles of chromate that precipitate will be related in this relationship. 2 moles of silver for every 1 mole of the chromate. So then I can do that math. That means 0.00100 moles of the chromate ion precipitated. Well, if that's what precipitated, we'll subtract that amount from what we had initially. If you go back in your notes, what we had initially was that 0.0700. So from that, we subtract 0.00100, because that's what's going to precipitate. And we get that we must still have 0.0690 moles of chromate running around in solution. We're going to take those moles and do like we did before, get it to molar concentration by dividing by 400 milliliters. 0.0690 moles of chromate in 400 milliliters of solution. To get to molarity, what we had to do before was introduce 1,000 milliliters over 1 liter. And then giving ourselves 3 sig figs. That would mean the molar concentration of the chromate ion is 0.173 moles per liter. Now this is at equilibrium now. This is not initial. So if that's at equilibrium, now we can kind of finesse the KSP expression for your silver chromate to get to the silver ion concentration by revisiting that equilibrium constant expression. So here's what that looks like. So this was our original KSP expression. We know now the chromate ion, which is 0.173 molar, and we're trying to get to the silver ion. And we've done this before. We can rearrange this expression, and the molar concentration of silver ion is going to be the KSP 1.1 times 10 to the negative 12 divided by the molar concentration of the chromate ion, CrO42 minus, all raised to the 1/2 power, or the square root of. Almost done. So we'll go ahead and substitute in our 0.173 for our chromate ion, and this is what we get. So at equilibrium, the silver left in solution is going to be the square root of quantity 1.1 times 10 to the minus 12 divided by 0.173. It's like we're only allowed 2 sig figs. So at equilibrium, the amount of silver ion you have left in there is 2.5 times 10 to the negative 6th molar, which is a pretty good premise. We said that all the silver ion will precipitate out. Well, we're almost done. So the amount remaining in solution, now we're almost done. All we got to do is take that molar concentration, use the volume to get to how much silver that must be. So here we go. The total volume is 400 milliliters of solution. We use the molarity we came up with. Oh, first we have to get that in liters, don't we? So we put 1 liter over 1,000 milliliters. And now we use the molarity we came up with, the non-flipped version, 2.5 times 10 to the negative 6th moles of silver per 1 liter of solution. And that will give us the silver running around there that's dissolved. 2 sig figs, 1.0 times 10 to the minus 6th moles. And then I think I have one last little thing down here to say, well, what percent is that then? So here's what that looks like. So we had 1.0 times 10 to the negative 6th remaining dissolved. Clear back several slides ago, you'll find out in our initial amount of silver, regarding the moles of silver, we had 0.00200 moles of silver starting out. If you divide that out to get to parts per 100, multiply by 100 or 100%, give us 2 sig figs. That means that only 0.050% remains in solution. It doesn't precipitate with the chromate. So probably of the two problems, it's one problem with 2 parts. Of the 2 parts, that first part is more likely what you're going to run into in your unit exam application. Second part, the extent of precipitation, probably not so much. Okay. All right, and this one, I will go ahead and just, I'll print it out and bring it Wednesday, but I'll also push out these next several slides for this third problem, so you can have it if you want to refer to it. But this one really, remember just a minute ago I said the second part, I'm not going to put on test. This one won't be on the test either. So this sort of problem, I hate these problems. Some problems you're like, oh, this is one of them. Okay. Any questions? All right. See you Wednesday.